Hello guys, Dr. Wesley here. Let's pray. Father God, we thank you, Lord, for this day. We thank you, Father God, for your goodness and your kindness towards us, Lord God. We pray, Father God, you bless this time, Lord God. Make this time yours, Lord God. Guide us this day, Lord God, this week, Father God, Father God, just make it the best week that we possibly can, Father God. Help us to be light to other people, Father God, who are in despair, who are in darkness, Lord God. Guide us this day, Lord God. Guide us, Father. We pray, Father God, that you would give me the words you would have me to speak, Lord God. Give us all listening ears. In Jesus' name, amen. Well, welcome back, guys. Let's get started. Let's not waste any time. We're going to be in chapter 5. Don't worry, I'm going to go back to section 4.2 and 4.3 and 4.4 at the end, but I really want to get some of this stuff down. So, and we'll talk about the vector spaces later on, probably at the end of this particular set of notes, okay? So vector spaces will be our last kind of big topic, and we'll be looking at different things that you can do with vector spaces, all right? So let's get started. We're in section 5.3. Okay, where we have orthogonal bases and subspaces. Orthogonal bases and subspaces. Now, last week we actually introduced the concept of a basis, right? If you guys remember that, we talked about how to what a basis is. We looked at the basis for a row space, column space, and node space. We figure out how to find a basis for any particular subspace that we have, right? Using the kind of this method of finding a basis for a row space. Now we're going to talk about orthogonal bases, so we need to give some definitions here. So a bunch of definitions, so topics for the day. Okay, topics for the day. It's going to be, what is an orthogonal basis? What is an orthogonal subspace or orthogonal subspace? And then we're going to look at projections. And this might be broken up into several videos, right? Of about 45 to 50 minutes in length. And they represent a day like Monday, Wednesday, Friday, if we were in class right now. Okay. Okay, so let's get started with our first definition. This is also in the PowerPoint. Definition. A set of vectors is called orthogonal when every pair of vectors is in the set orthogonal. Okay. Kind of the standard one that people are used to seeing, one that's pretty straightforward, is the set of vectors from our standard basis, where we have 1, 0, 0, 0, 1, 0, 0, 0, 1, right? This is a standard basis in R3. Standard basis in R3. However, what happens when I take the dot product of any of these vectors, right? If I take the dot product of any of these vectors, 1, 0, 0, dotted with 0, 1, 0, I get 0, right? And if I take 1, 0, 0, dotted with 0, 0, 1, that's 0. And do I have one more? Yeah, I have 0, 1, 0, dotted with 0, 0, 1, that is also 0. So we can say that each one of these vectors is, each pair of these vectors is orthogonal to, when I pair these vectors together in S, all those vectors are going to have a dot product of 0, which means that they're orthogonal to each other, right? So that means that this set S is orthogonal. Set S is orthogonal. Next definition that we have here. So we call this an orthogonal set of vectors. I'll put the next definition up here. If each vector of the orthogonal set is a unit vector. Okay. What do we mean by a unit vector? Remember what a unit vector is. A unit vector is a vector whose magnitude is equal to 1, right? So if each vector of the orthogonal set, right, if I have an orthogonal set, if each vector in the orthogonal set is a unit vector, then the set is orthonormal. Orthonormal, right? So it has the orthogonal part, ortho, right? It has the normal point, meaning a magnitude of 1, right? Remember the norm, magnitude of 1. So orthonormal. And guess what? The last one we got you doing was also an orthonormal set because, right? If I look at each one of these guys using the previous example, okay, using this previous example right here, if I take the magnitude of each one of these vectors, that's 1. The magnitude of this vector is also 1. And the magnitude of the last vector is also 1. We found out last time, right, previously, that this is an orthogonal set. It's orthogonal, and the magnitudes of each one of these vectors is 1, right? So that means that S is also an orthonormal set. S is also an orthonormal set. So not only is it an orthogonal set, right? Orthogonal meaning that when I take the dot product of any pair of vectors, I get 0, but it's an orthonormal set as well. So it's an orthogonal set and orthonormal set. And usually if we say orthonormal set, we mean that it is orthogonal and has unit vectors, from every single vector in the set. Each vector in the set is a unit vector. I should say it that way. And I'm going to have here a note that we have here. Note. An orthogonal or orthonormal set of vectors is always a linearly independent set. So if I have a set of vectors that is orthogonal, then I automatically know that that set of vectors is linearly independent. I don't have to check for linear independence of an orthogonal set. I know that if the set is orthogonal, it's automatically linearly independent. Likewise, if the set is orthonormal, right, which means orthogonal and the vectors are all unit vectors, then that set is also linearly independent. Okay. And one more thing, one more definition. Oh, well, actually, I shouldn't say one more definition. Two more definitions. Two more definitions. If S is also, so if the orthogonal should say in the orthogonal or orthonormal set is a basis for a subspace in Rn. Then the set is called an orthogonal or orthonormal basis of the subspace, respectively. So if the orthogonal or orthonormal set is a basis for a subspace in Rn, remember that my subspace could be the entire space Rn itself, or it could be a plane or a line or something like that. But whatever it is, if I have a set of vectors and it is a basis for a subspace in Rn, then we can call that an orthogonal or orthonormal basis of that subspace. So I can say I have an orthogonal or orthonormal basis for Rn if I have a basis for Rn that's orthogonal or orthonormal. So for example, if we look at this last one here, S equal to 1, 0, 0, 0, 1, 0, 0, 0, 1 is a basis for R3, right? We know that this set is a basis for R3. We've already seen this before, it's the standard basis. However, we also know that this basis is orthogonal, actually we know it's orthonormal. We know that this set of vectors is orthonormal. So therefore, I can say this set is orthonormal. Orthonormal. Therefore, S is a orthonormal basis. S is an orthonormal basis. Oh, I forgot to put my last squiggly over here. There we go. Perfect. Right, so S is a basis for R3. This set is orthonormal, therefore S is an orthonormal basis. Okay. And this is something that we've already said before many times. I have it in my notes, but it bears repeating. And it says this: if a set of, if S, and S is just a name, it's not this S, I can call this anything. But I'll say this: if S is a set of linearly independent vectors, in Rn, then S is a basis for Rn. Okay. Now we've already said this before, and again, I want to reiterate the fact that this S is not necessarily this S. S is just a set of linearly independent vectors. Oh, set of n linearly independent vectors. Of n. The set of n linearly. Let me just erase that. Set of n linearly independent vectors. So if S is a set of n linearly independent vectors in Rn, then S is a basis for Rn. Again, I want to reiterate the fact that this S is not the same as this S. S is just a set of n linearly independent vectors. So if I was in R4 and S was a set of any 4 linearly independent vectors, then those 4 linearly independent vectors would form a basis for R4. Now I have a couple of examples I want to look at and talk about. I'm going to erase this stuff here. Got some juice in this one. Here's my examples there again in the PowerPoint. Here I have that S equal to 2, 4, negative 4, 2 is an orthogonal basis. In R2. Here I have S equal to, my set of vectors S is 2, 4, 4, negative 2 is an orthogonal basis in R2. Now why do I say that this set is an orthogonal basis? Well, let's see if they're orthogonal to each other. Let's check that out first. We'll say orthogonal. I'm assuming that it is orthogonal basis. Orthogonal. So if I take 2, 4, dot it with negative 4, 2, I get negative 8 plus 8, which is 0. So these two vectors are orthogonal to each other. Since these two vectors are orthogonal, yes, since these two vectors are orthogonal, that means that these two vectors must be linearly independent. That's what we just said before. Whenever we have a set of vectors that are orthogonal to each other, then that means that that set of vectors is linearly independent. So this set of vectors are linearly independent. So I have S has 2 linearly independent vectors. Okay. Since S has 2 linearly independent vectors, how many linearly independent vectors do I need to be a basis? Well, how many linearly independent vectors do I need to be a basis for R2? How many vectors do I need to be a basis for R2? I just need 2 basis vectors, right? S has 2 linearly independent vectors. So since S has 2 linearly independent vectors, then S must be a basis for R2. A basis for R. Now, I have to be careful here, right? The vectors that I'm looking at have to be in R2, right? So I have 2 linearly independent vectors in R2. Those 2 linearly independent vectors in R2 create a basis for R2. Okay. So therefore, it is orthogonal and it is a basis. So since it's orthogonal and it is a basis, that means that it is an orthogonal basis. Hopefully I'm not over-explaining that. Okay. Let's look at one more. I've already talked about the standard basis. Here's another one. I have S equal to 1, 0, 1, 0, 1, 1, 0, 0, 1 is not an orthogonal basis. It's not an orthogonal basis. right? How do I know it's not an orthogonal basis? Well, if it's an orthogonal basis, right, or an orthonormal basis, if it's an orthogonal basis, then I should be able to take the dot product of any two of these guys. So I'll take the dot product 1, 0, 1, dotted with 0, 1, 1. If I take the dot product of these two, right, this is 0 plus 0 plus 1, I believe, okay, 1. That does not equal 0, by the way. So it doesn't equal 0. That doesn't equal 0, so therefore S is not an orthogonal base. S is not an orthogonal set. S is not an orthogonal set. Now I don't have to check. I don't have to check at all to see if it's an orthonormal set, right? Because if it's not an orthogonal set, it's definitely not going to be an orthonormal set, because orthonormal just adds one more condition on top of an orthogonal set, right? So this S is not an orthogonal set, so it's not going to be an orthogonal basis. But is S a basis? Is S a basis? And the answer is S is a basis, right? I can say that. However, S is a basis. We already know how to find whether something is a basis or not, right? It has to be linearly independent. Are these three vectors linearly independent? The answer is yes, they are. These three vectors are linearly independent. So I can say that, however, S is a basis. It's not an orthogonal basis. It's not an orthogonal basis. It's not an orthonormal basis, but it is a basis because I have three linearly independent vectors. It's an orthogonal, S is not an orthogonal basis for, I should say, for what space? For R3. But S is a basis for R3. It's not an orthogonal basis, but it is a basis for R3. So that's what I want to say. Let me repeat that again. S, this set of vectors, these three vectors here, right? They are not orthogonal to each other. However, they are all three linearly independent. Since they all three of these guys are linearly independent, then that means that this is a basis for R3, right? Because these three vectors are in R3. Let's switch gears and talk about orthogonal subspaces. Orthogonal subspaces. In definition that we have here, two subspaces of Rn are orthogonal when the vectors in each subspace are orthogonal. I should say the vectors in one subspace are orthogonal to the vectors in the other subspace. Okay. So here we say that two subspaces are orthogonal when the vectors in one subspace are orthogonal to the vectors in the other subspace. So I have two subspaces. And the vectors, the basis, we can think of these as the basis vectors. We can just look at the basis vectors. If the basis vectors of one subspace are orthogonal to the basis vectors of the other subspace, we say that those two subspaces are orthogonal to each other. Because the basis vectors form a foundation for every vector in that particular subspace, right? Remember that the basis vectors generate every other vector in the subspace. So if I have the basis vectors on one subspace, and I have the basis vectors of another subspace, and those basis vectors are orthogonal to each other, then we can say that those two subspaces are orthogonal to each other. Okay. One easy example of this is given by looking at, let's say, we'll call this one S1, we'll call this our subspace. We'll have two subspaces. And we're going to be in R3. Okay. And so suppose that S1 is going to be the subspace spanned by the vectors 1, 0, 0, and 0, 0, 1. Okay. So one subspace is spanned by the vectors 1, 0, 0, and 0, 0, 1. It's going to be a plane. And let me just call them, I just say it's a span. We'll just say S1 is the subspace, 1, 0, 0, and 0, 0, 1. Okay. So this is going to give me a plane in space. And so this is a plane in R3. Okay. And we'll say that S2 is spanned by just a single vector, 1, 0, 1, 0. And this is a line in R3. Okay. So S1 is going to represent a plane in R3. S2 is going to represent a line in R3, right? So we're looking at these are my two subspaces. And we want to know, are these two subspaces orthogonal to each other? And the answer is yes, they are. Note that when I do this, I don't check to see if the vectors inside the subspace are orthogonal. I just want to check to see if the vectors of S1, the basis vectors of S1, are they orthogonal to the basis vectors of S2. So I'm going to check this. Is 1, 0, 0 orthogonal to 0, 1, 0? And the answer is yes, they are. And is 1, 0, 0, 1 orthogonal to 0, 1, 0? And the answer is yes, it is. Both of these guys check out. They're both orthogonal. 1, 0, 0 dotted with 0, 1, 0 is 0, and 0, 0, 1 dotted with 0, 0, 1 is 0 as well. So these basis vectors in S1 are orthogonal to this basis vector in S2, right? So we can say that yes, S1 is orthogonal to S2. S1 is orthogonal to S2. And you guys have seen this type of thing before if you've taken calculus 3, right? I can think about this as a plane in space, right? And you can think of S2 as the normal line, right? Normal line going through the plane, right? The normal line is perpendicular to the plane. If you guys remember that from Calc 3. The normal line is perpendicular to the plane. So this is kind of an example of how that would be, right? Let's look at another example. Oh, before we look at another example, let me, let's just dive into another example. So let S1 and S2 be subspaces in R4, where S1 is going to be equal to the span of 1, 2, 0, 3, 0, 0, 1, 1. It's going to be S1. S2 is equal to the span of -2, 1, -2, -2, 1, 0, 0. -3, 0, -1, 1. Okay. The subspaces are orthogonal. The subspaces are orthogonal. Now, just to kind of let you know, I want you guys to notice that these vectors in S1 are linearly independent. Okay? Are these vectors necessarily orthogonal to each other? No, they're not. These two vectors are not orthogonal to each other, right? That's okay, because we're not trying to check to see if S1 is an orthogonal set, right? I'm not trying to check to see if these vectors are an orthogonal set. That's not what I'm trying to find out. I'm trying to find out, is S1 orthogonal to S2? And with S2, these vectors are also linearly independent, right? These vectors are also linearly independent, right? So these represent basis vectors. So here I'm dealing with two planes in R4. I'm dealing with two planes in R4, and I want to know, are those two planes in R4, are they orthogonal to each other? This is what I want to know. Are the two planes in R4 orthogonal to each other? And to do that, I need to check all possible combinations of the vectors of S1 with the vectors of S2. So let's do that. I'm going to take 1, 2, 0, 3, dotted with -2, 1, 0, 0. I'm going to take 1, 2, 0, 3, dotted with -3, 0, -1, 1. I'm going to take 0, 0, 1, 1, dotted with -2, 1, 0, 0. All right. And the last one, I'm going to take 0, 0, 1, 1, dotted with -3, 0, -1, 1. Okay. So my guys. So when I take the dot product of each one of these, I'm a little bit scared now. Does it work out? I don't know. If I do this one, I get, what's that? -2 plus 2 equal to 0. Oh, that's good. Oh. The next one I get was that -3. This is going to be 0. This is going to be 0 plus 3. That's 0. Okay. This is going to be 0, 0, 0, 0. So that's 0. And this is going to be 0, 0, -1 plus 1. That's 0. So the vectors in S1 are orthogonal to the vectors of S2. So we can say that, yes, S1 is orthogonal to S2. We're dealing with an orthogonal subspace. So we're in R4, right? And these planes are perpendicular to each other, right? They're perpendicular to each other in R4. Very good. I hope that kind of makes sense. So let me give you a couple more definitions. Just definitions upon definitions upon definitions. Seems like it never ends sometimes, but there's always an end. There's a light at the end of the tunnel. Not a train. Some of you guys are saying that. If S is a subspace of Rn, okay? If S is a subspace of Rn, then the set of all vectors orthogonal to S is called the orthogonal complement of S. Well, underline that. Orthogonal complement of S denoted S, and I'm going to use the perpendicular sign that I used over there, right? This perpendicular sign, the one that we've used before. S perp. That's what we call it. S perp. S perp. So if S is a subspace of Rn, then the set of all vectors orthogonal to S is called the orthogonal complement of S, denoted S perp. And S perp is also a subspace of Rn. Actually, our last example is an example of this orthogonal complement idea. In our last example, S1 and S2 are orthogonal complements of each other. So I'm going to say that. In our last example, S1 and S2 are orthogonal complements. Meaning that the set of vectors that are orthogonal to S1, all the vectors that are orthogonal to S1 are going to be along the plane S2. And all vectors orthogonal to S2 are going to be along the plane S1. Okay. These guys are orthogonal complements of each other. And we have a little bit of notation. I'm going to put here notes. We don't really use it here, but it's kind of cute to know this. S perp is equal to S. So the orthogonal complement of the orthogonal complement of S is S itself. So I'll get back my original subspace. And last but not least, for Rn, let S be a subspace in Rn, and S perp is orthogonal complement. Okay. So let S be a subspace in Rn, and S perp is orthogonal complement. So if we have this on any subspace, it doesn't matter what subspace it is, as long as there's some subspace in Rn. And then let S perp be the orthogonal complement of S. Okay. Then, I'm going to put a comma here. The span of the union of the basis vectors of S and S perp is Rn. So if you combine the basis vectors of S and S perp, doesn't matter what basis vectors you pick, as long as you pick a basis for S and a basis for S perp, if you combine those basis vectors together, that combined span of those basis vectors is going to be all of Rn. So I can say, if I wanted to, I'm going to squeeze it in here. Notice from our last example, the last example that we did for the class, I mean, not for the class, last example that we just got to doing right now. The last example we did was R4, right? I have S1 and S2, these guys are orthogonal complements. What I can do is I can combine them together as one set. And And I can say that R4 is equal to the span of those combined basis vectors of S1 and S2. So 1, 2, 0, 3. 0, 0, 1, 1. Negative 2, 1, 0, 0. Negative 3, 0, negative 1, 1. The span of all four of these vectors from S1 and S2 is going to be R4. And that is pretty neat. That's pretty interesting stuff. And those of you guys who've taken calculus 3, you've seen this before, right? Where we have a vector in R and then in R2, and then we find its orthogonal vector, right? If you combine both of those vectors together, you can get to any point in R2. So this is kind of an extension of that same idea. So we've introduced this idea of orthogonal sets, orthonormal sets. We then introduced the idea of orthonormal basis and orthogonal basis, right? So we got that in our brains. Then we introduced the idea of orthogonal subspace, right? And that's a subspace. We have two subspaces that are orthogonal to each other, right? We just check their basis vectors to see if the basis vectors are orthogonal. That's enough to be able to do that. And now what we want to do is we want to talk about fundamental orthogonal subspaces. Let's talk about some of the fundamental orthogonal subspaces of matrices. Okay. So let's talk about some of these fundamental, well-known orthogonal subspaces. So fundamental subspaces. Of a matrix. And the fundamental subspaces of a matrix A, we'll just say a matrix A, is going to be the row space of A. Okay. The column space of A. The node space of A. You're like, Dr. Wesley, that's just 3. But we can also do the node space of A transpose. I don't need to put down the row space of A transpose because the row space of A transpose is just the column space of A. I don't have to put down the column space of A transpose because the column space of A transpose is a row space of A. Woo, say that 5 times fast. Right? So these are my 4 fundamental subspaces of a matrix A. The row space of A, the column space of A, the node space of A, and the node space of A transpose. These are my fundamental subspaces of a matrix. And these guys, some of these guys are orthogonal complements of each other. Or orthogonal subspaces, I should say. Well, they are orthogonal complements. They're orthogonal subspaces. So if A is a m by n matrix, then 1, the row space of A and the node space of A are orthogonal subspaces. And they're actually orthogonal complements of Rn. So the vectors of the row space of A are always orthogonal to the vectors of the node space of A. 2, you probably know where I'm going to go with this one. The column space of A and the node space of A transpose are orthogonal complements, or orthogonal subspaces in this case. Orthogonal complement says something a little bit stronger, meaning that I've got all of the vectors that are orthogonal to the column space are going to be in the null space of A transpose. That's what we mean by orthogonal complement. These guys are orthogonal subspaces, but they're also more strongly orthogonal complements of each other. So the column space of A and the null space of A transpose are orthogonal subspaces of Rn, which is really neat. And because we have these fundamental subspaces where we know that the row space of A is equal to the null space of A transpose, and actually that these guys are orthogonal complements of each other. Because we know this, we can use this relationship between the row space and the null space to be able to come up with any orthogonal complement of a subspace. So if you tell me what a subspace is and you give me the basis vectors of that subspace, okay, then I can always tell you what is the orthogonal complement of that subspace using this relationship I have between the row space of A and the null space of A. Let's look at an example. Let's talk about that. Actually, let me write down the steps first. Just erasing this stuff, getting it out of the way. Well, let's do this by doing an example, just to save a little bit of space. I want to find the basis of an orthogonal complement of S. I want to find the basis of an orthogonal complement of S. And we're going to just kind of do this by an example. I kind of have the steps right here, but I'm going to incorporate the steps inside of the problem. So let's look at the example. I'm going to put here S equal to span, okay, of the vectors 2, 2, -1, 0, and 1. 2, 2, -1, 0, 1. -1, -1, 2, -3, and 1. Okay, so it's -1, -1, 2, -3, and 1. This, I have a really small print here. I'm using my PowerPoint slides here. And then I have here 1, 1, -2, 0, -1. And the last one I have is 0, 0, 1, 1, 1. And this is in R5. And I want to find S perp. I want to find S perp. So I have let S equal the span of these 4 vectors in R5, right? And I want to find what S perp is going to be, right? What's the orthogonal complement? What's the orthogonal complement of this? And to be able to find an orthogonal complement, what I'm going to do is I'm going to do just like I did before. I'm going to create a matrix A using the vectors as rows of my matrix. So step 1, create a matrix A using the vectors as rows of A. So let's do that. So So I have A equal to, I'll create my vector. Here, my matrix, I have 2, 2, negative 1, 0, 1. Negative 1, negative 1, 2, negative 3, 1. 1, 1, negative 2, 0, negative 1. 0, 0, 1, 1, 1. So I'm going to create a matrix A using the vectors as rows of A. This is my matrix A. Then I say, okay, remember, again, I want to use this idea. I want to use this idea that the row space of A and the node space of A are orthogonal complements. Essentially what I did is now, this is essentially my row space of A. Okay? This span of these vectors is just the row space of A, right? Because I put them in as rows of A. This is the row space of A, okay? And what do we know that the row space of A is orthogonal to? It's orthogonal to the node space of A. So what we're going to do, step 2. I'm going to find the node space of A. Because the node space of A is orthogonal to the row space of A. So I'm finding node space of A. So remember again that essentially I'm solving AX is equal to 0 for X, right? So essentially I'm just adding a column of zeros at the end. I'm going to do reduced row echelon form on A. If I take the reduced row echelon form of A, I get 1, 1, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0. And then I have a row of zeros. Now notice, so this is going, so my node space of A is going to be, I still need to solve for it, right? But this is my reduced row echelon form of A, and remember I'm solving for A is equal to 0, so I have another column of zeros. You can either tack it on when you do your matrix, so just leave it out. It doesn't really matter. Before we go on though, before we continue, I want to just kind of talk about this for a second, right? What is the dimension of S? What's the dimension of S now? Can you tell what the dimension of S is going to be in this case? Right? When we took the reduced row echelon form of this, right? We got rid of all the rows that we didn't need, all the vectors we didn't need, only left with the ones that we did need, right? So you don't have to do this, but I'm going to put it right here. S, right? S is equal to the span. Let's see if I can squeeze it in here. I just do it on the side of 1, 1, 0, 0, 1, 0, 0, 1, 0, 1, and the last one is 0, 0, 0, 1, 0. Okay. S, when it comes down to it, I don't need all 4 of these vectors, I only need 3. The dimension of S in this case is 3. It's a 3-dimensional shape, right, in R5. It's a 3 space in R5. All right, so I just wanted to say that, I just wanted to kind of put that out there, right? That S is going to be given by these 3 non-zero rows, right? Span of those 3 non-zero rows. So S is just going to be a 3 space in R5. Right, so let's go back to step number 2. So that was a little bit of a aside there, just a little bit. So I want to find the node space of A, right? So I need to create my system. So I have, what's that, x1 plus x2 plus x5, x3, x4, x5 is equal to 0. Here I have x3 plus x5 is equal to 0, right? And then I have x4 is equal to 0. What's my solution look like? Let's put it in parametric form first. Solution. Now x1, x2, x3, x4, x5. X1, x2, x3, x4, x5. X4 has to be 0. What are my free variables? If you said x1, x3, no, sorry, what are my leading variables? What are my leading variables? My leading variables are x1 and x3, x4, okay? x2 and x5 have to be, are my parameters, they're my free variables. They're free to be wherever they want to be. I'll call x2 S or R, or what should we call it? We'll call it S. x5 we can call T. So x1 is equal to, I think, what's that, negative S minus T. x3 is equal to minus T, right? And I need more space. Where's that? So if I write this in vector form, I have x1, x2, x3, x4, and x5, right? I have two vectors that I'm going to create, one for S and one for T. S, I get, what is that? What do I have inside? Negative 1, what's that? 0, 0, 0, I think. Yeah, I think that's right. What's the other one? T is going to be negative 1, 0, 1, 0, 0. Nope, that's not right. 1, 0, 1. And you're screaming at me. I hear you. I hear you. Hear you. No, did I do it right? Yeah, I'm fine. I thought you guys were screaming at me. You weren't screaming at me. Thank you. Thank you. I think I did that right. Let me double check. Yes, that's what I have in my notes. Oh, negative 1. That's what you guys are screaming at me about. Thank you. So negative 1, 0, negative 1, 0, 1. And so this is going to, my null space is a plane in R5, right? It's a plane in R5. And my vectors for the null space of A, it's going to be the span of these two vectors. And I just erased what we had before, but the row space of A, and the null space of A are orthogonal complements of each other, right? So we saw what the row space of A is going to be. It's going to be given by these three vectors, right? Or by this, right? Either one. Those vectors have to be orthogonal to the null space of A. So guess what? Step 3. Step 3 is that the S perp is equal to the null space of A. So you really don't have to do anything in step 3. Step 3 is really nothing at all. S perp is equal to, in this case, the span of these two vectors. Now, I want you guys to know that if I were to combine S and S perp together, combine their basis vectors together, right? That combined set of basis vectors would span all of R5. So if I were to grab these vectors with these vectors, or this set of vectors, right? It doesn't matter which one of these. I like this one better. Add these guys together, put them together as a union of the set of vectors, span using these 5 vectors, 1, 2, 3, 4, 5. If I use all 5 vectors Find the all possible linear combinations of that, and all possible linear combinations of that would be all of R5. Okay. Whew, that's a lot there, right? Very good. You guys are doing well. Doing well. Let's stop here, and then I'm going to pick up with the next topic.